Okay, so in that section, the section 2.1 of Griffiths book, third edition, there is an example that is solved and which I would like solved in the book, which I would like to solve now with you, is the example 2.1. So what they give to us is already the wave function at time zero, already written as a superposition of those solutions of the time-independent Schrödinger's equation. And this is the wave function at time zero. Okay, so remembering the recipe, we first would have to obtain the wave functions, the part for the time-independent Schrödinger's equation. Then with the initial state, we would have to find those components. But all that is already given, it's already done for us. Okay, so we already have this initial state in terms of the solutions, the solutions of the time-independent Schrödinger equation. We already have it in terms of those coefficients. Okay, so, and it's a very simple case. We have just this linear combination of just two cases, of just two stationary states. Okay, let's also assume, just to make our life easier, that these components, these coefficients, they are real. It could be complex, but let's assume that they are real, and that the psi1 and the psi2 also could be complex, but let's assume that they are real, okay, for this problem. And what is the problem? Well, they want us to find the wave function later in time. Very well. And once we have that, we want to find the probability density, which is the absolute square of that. All right, so how do we do that? We already have the initial state written in terms of this psi1, psi2. So what is going to be the wave function at any time t? All that we have to do is we pick each one of those terms in our linear combination, in our sum. In our case, we just have two. We pick each one of them and attach to it that time dependence, that exponential with the corresponding energy. Okay? Okay, so this I did for the 1, and now for the 2, for the psi2, I have exponential minus I energy 2 t over h bar. Okay, we are done. So you see, it's simple. Now comes the second part, which is let's now obtain the probability density. All right, so how are we going to do that? Well, the conjugate and the function. The conjugate is, in principle, C1 should be conjugate, no, but since it's real, I'm just going to put C1. Psi1, in principle, should be the conjugate. No? So what I'm saying is, in principle, we should put the star here, but since we are assuming that they are real, I don't need to do that. But when I come to the exponential, well, I is I, no, is the imaginary unit. That one will become plus, okay? So I, energy, time, and h bar. The other one, same story, C2, psi2, in principle, we should put the star from conjugate. We are not, because we are assuming it's real. But when it comes to the exponential, yes, don't forget to change to plus. I e2 t over h bar. All that multiplied by this term here. Okay, I don't have space, but just write it back there. All right, so now what we're going to do? Well, this term multiplied by this term gives us C1 square, psi1 square. If we had played with the conjugate, as we said, just for you to keep it in mind, this would be C1 absolute value square, psi1 absolute value square, okay? This is important. Well, we are simplifying in this problem, assuming that they are real, okay? But so C1 square, psi1 square, very good. What happens with the exponential part? Well, this plus I and this minus I gives us exponential of 0, which is 1. I don't need to write number 1. Okay, then comes this term now multiplied by this one. So now we have C1 and C2, psi1 and psi2. And things do not cancel now in the exponential. So we have exponential of plus I E1 minus E2. Yeah, so you see, I pick the E1 from here with a plus sign and the E2 from here with a minus sign. And the rest is present in both terms. Okay, now let's start with this guy. So here and multiply with that one. So now we have, again, C1 and C2, psi1 and psi2. And now careful, because the exponential for the E1 is negative, okay? So I will put here exponential of minus I, because E1 is negative, so E1 minus E2, and the rest is E, okay? And then finally, the two last terms, so it will be C2 squared and psi2 squared. The exponential now cancel is the same energy. One is plus I and the other one minus I. So that's it. All right. So you see what we were saying. When we have a general state, not a stationary state, the probability density is not a constant as we have for stationary states. And you see here that it has a dependence on time. Let me rewrite these things and see if you recognize what we have there. What is this time dependence? Let me pick the C1 and the psi1 square, and this other one, the C2 square and psi2 square. And now let's focus on these terms here, which depend on time. So let's see how we can write them. Both have C1 and C2, psi1 and psi2, right? And one is exponential plus I E1 minus E2 t over h bar. The other one is plus, now exponential minus I E1 minus E2 t over h bar. Stare a little bit at this. Do you recognize a sum of two exponentials with one is plus I, the other one is minus I? Do you recognize what function this is? Let me make it perhaps even more evident. Let me multiply and divide this by 2. Do you recognize now what we have here? We have a cosine, isn't it? Cosine of E1 minus E2 multiplied by time divided by H1. Eh? Okay, so then we now can put our probability density in a final form, in an elegant way. So we have C1 squared psi1 squared. We have C2 squared psi2 squared. And here we have 2 C1, C2, psi1, psi2, cosine. Cosine of this difference in energy. Yeah, so we have a probability density that is oscillating, that is following this sinusoidal function. It's oscillating. What is the frequency of these oscillations? This frequency of this oscillation is that it doesn't matter. You can either write E1 minus E2 divided by h bar, or it's the same thing, E2 minus E1 divided by h bar, because the cosine of x is equal to the cosine of minus x. So it doesn't matter which order you pick. The important thing is that the frequency is given by the difference in the energies of these stationary states. Okay, so this is the end of this problem.